Lesson 3 is going to be all about number theory, so let's get started. So in math counts, we're going to deal with a lot of number theory, which is the study of integers. Number theory. Now, number theory is a big part of math counts. You're going to get lots of problems involving odd integers, primes, composites, all sorts of stuff. So it's important you know some basic rules. Now, to test if a number is prime or not, you just take, let's say we have a number x, we want to test if it's prime. All we need to do is test the primes up to the square root of x. Every single prime up to the square root of x. So, like, if I wanted to test if, let's say I want to test if the number 15 is prime. Number 15, so we take the square root of 15, which you estimate. You're not going to actually simplify the radical to the nearest integer. Now, note how we're going to find a number which squares near 15. So, perfect squares near 15. 16 is a perfect square. 16, 15, 14, 13, 12, 11, 10, 9. 9 is a perfect square. So we know that 9 is less than 15. However, we also know that a number greater than 15 would be considered something like 16. Square root of 15 would be 16. So, all we need to do are test the primes. Now, we can already just test some primes, so let's go down. Let's go down the list. Let's go to 9. Now, 9 is not divisible by 15. Or 9 doesn't go into 15. So we go to 8, no. 7, no. 6, no. 5, yes. So 15 is not prime. And that's how you would test if a number is prime or not. Now that's testing if a number is prime or not. You have to know the basics of odd and even integers. Your even integers are like 2, 4, 6, 8. Your odd integers are 1, 3, 5, 7, 9. So those are your even and odd integers. I'm pretty sure you already know them. And note that every single even integer is a multiple of 2. Since we're counting by 2's and we're going even integers. Now, there's no such rule for odd integers. We do count by 2 as an odd integer, but we start at 1. In even, we start at 0. And we count by 2's. But 0 is not a multiple of 2. Remember that even though 0 is considered even, the 0 is not a multiple of 2. So keep that in mind. That's basically all the basics of number theory you need to know for math counts. So let's go and take a look at some problems. Okay. So, a group of 25 pennies is arranged into 3 piles such that each pile contains a different prime number of pennies. What is the greatest number of pennies possible in each of the 3 piles? Credit goes to the math counts competition for this. All credits goes to math counts for this problem. So we have 25 pennies, which is divided up into 3 piles, but each pile contains a different number of prime pennies. Now, what is the greatest number of pennies possible in each of the 3 piles? The way we're going to take a look at this problem is we're going to test the greatest prime possible and work our way down. Now, what is the greatest prime from 25 to 0? It's 23. So let's test 23. 23 minus 5 is, or 25 minus 23 is 2. Now we need to break up 2 into a sum of primes. 2 cannot be broken down to a sum of primes. We have 1 plus 1, but 1 is not prime. So we know that 23 is not possible. Let's move on to the next prime. Next largest prime. 22, 21, 20, 19 is the next largest prime. Now we need to first, 25 minus 19 is 6. We need to break 6 down to a sum of primes. Now we can have 1 and 5. 1 is not prime. We can have 2 and 4. 2 and 4. 2 is prime, but 4 is not. And now we can have 3 and 3. And you might just go ahead and say, oh, it's 19. Read the question. We want every single pile to have a different prime number of pennies. So let's move on. 3 plus 3 we can have, and then we just go into 4 plus 2. So 19 is not a possible case. Let's move on to the next one. 17. Now, we need to compute 25 minus 17. 25 minus 17, that's just 8. And we need to break 8 up to a sum of primes. 1 and 7, 1 is not prime. We can have 2 and 6, 6 is not prime. We can have 3 and 5, 3 is prime. We see a possible case. We have 17, we have 3, and we have 5. All are different primes, and they sum to 25. So we can have a group of 17, a group of 3, and a group of 5. And these these make up the 25 pennies, and each of them are prime, and they're different. And we see that 17 is the largest possible prime that can be in each of the 3 piles. You know, we can move our terms around. We can have 17 can go over here, but it doesn't matter where 17 is. All we're looking for is the greatest number of pennies possible in each of the 3 piles, which we can see is just 17. Is our answer. Now let's move on to the next problem. What is the 40th positive odd integer? This is the 2020 Math Counts School Sprint Round competition. All problem credits goes to Math Counts. Now we're looking for the 40th positive odd integer. Now you might just start counting until you reach the 40th positive odd integer, but that's going to take too much time. If you've done Math Counts before, you probably know that it's a timed examination. You can't spend the entire day trying to find the 40th positive odd integer, especially since this problem was one of the middle section of the problems, or middle to beginning section of the problems. Now we need to quickly build up a formula or some way to quickly find the 40th positive odd integer, because there's no way to find positive odd integers just like that. Well, there is a way, and we're going to find that way right now. First, what is the second positive odd integer? We're going to start small. Second positive odd integer. Second positive odd integer. We know that the odd integers are 1, 3. So our answer is 3. But how do we get to 3? Second, I think of 2. And I want second positive odd integer. Think of how we can get there. Second positive odd integer. Well, I can multiply this by 2. And I can get 4. 4 minus 1 is 3. So that's one way I can get to there. But does this work for every single time? Let's find out. We'll see if this works every single time. Let's try to find the third positive odd integer, which is 1. It's 5. let's see if we can use our old method to get the third positive odd integer. Now 135, that's a third positive odd integer. When I think of third, I think of 3, and I'm going to multiply it by 2. That's the same thing we did last time. 3 times 2 is 6, minus 1 gives us the 5. So that's one way that we're seeing that we're getting it every single time. Now, let's try something a little bit bigger. Let's try the 10th positive odd integer. I'm going to erase a lot of this, and we're going to find the 10th positive odd integer and see if our method works for a little larger number. 10th positive odd integer. Alright, the 10th positive odd integer. Now, let's use our method first. When I think of 10th, I think of 10. I multiply by 2, I get 20. Subtract off a 1, 20 minus 1, that's 19. Now 19 is odd, but let's see if it's the 10th positive odd integer. Let's start listing them out. 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. Now let's count. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So our method is clearly working. Now let's just use it on our problem. Our problem is we're attempting to find the 40th positive odd integer. Now when I think of 40th, I think I use 40, and I use my same thing. I multiplied by 2. 40 times 2 is 80, and by our formula that we built, we can just do 80 minus 1 to get 79 as our final answer. And that's another strategy in these problems, is to turn a large problem into a small and a simpler problem, and then try to solve that problem and build a formula or build equations. And that's the main strategy we've used throughout these problems. In this problem, we use what's called range. We narrowed our range down by starting from the top and then using strategic guessing until we got to our answer. And a lot of the times this works for number 3 problems. So hopefully this video is helpful, and yeah, that's part 1, number theory, class 3 of math counts preparation.